The entire eclipse, as you see right here, is from the beginning time it enters the penumbra till it finally leaves the penumbra. It's actually quite long. It's 5 hours and 11 minutes. But we normally don't see the eclipse at that point. We usually are more used to this point right here when we're measuring it from the first time it goes into the umbra to the last time it leaves the umbra. And that's called the umbral eclipse, and it takes about 3 hours, a little over 3 hours, 3 hours and 16 minutes for that to happen. And the total eclipse period, when it's totally in the umbra, the total eclipse period is about a little over an hour and 1 minute for this eclipse. So that's kind of the skinny on this particular eclipse.
And that bullseye, Ron, that's actually a cross section, like a slice of a cone of shadow that extends. That's Earth's shadow extending 870,000 miles out into space.
Right.
And if you sliced it right about where the moon is, which is about 230 plus thousand miles, we'll get to what that actual distance is tonight, you would see this bullseye, and that dark heart bullseye is where you would absolutely not see any sunlight.
That's right. So if we kind of take a side view of this and we watch the moon actually move through the shadow of the Earth, here you see the moon over on the right-hand side of the slide. Let's get it in motion here. So the moon is moving along there. Now notice that the moon is moving along the green line. That's the orbit of the moon around the Earth. The white line through the center of the slide here is the orbit of the Earth, or the path of our shadow, two ways of looking at it. Now the moon is about to cross over from south of that path, called the ecliptic, to the north part. It's tilted 5 degrees, and now it's in the penumbra, and now it's in the umbra. But you'll notice that that green path is tilted 5.1 degrees to the path of the Earth's shadow, which is also the path of the sun as we see it in the sky around the Earth.
We call that the ecliptic.
The ecliptic. We know that the sun really doesn't move around the Earth's moving around the sun, but it's like going around a campfire. When you walk around a campfire, you see the campfire move against the background, and that's sort of what we see here on the Earth. I guess we can look at that geometry a little bit closer. That point where the moon's orbit seems to cross over the ecliptic is called the node. And there's 2 nodes. There's one on each side of the sky. This one, where the moon goes from below the ecliptic to above the ecliptic, is called the ascending node. And the one on the other side, which I'm not showing here, is where the moon then dives back down below the ecliptic, and that's the descending node. But if we look here, there's actually a limit. Since the moon's path is tilted to the ecliptic, to the path of the shadow, it has to be within a certain distance of that crossing point. Otherwise, it will not be in the shadow of the Earth. It'll be too far away. So if we label that, here it is with the path of the path of the moon and the 2 limits. So these 2 circles, you can't get any farther from the node here and have the moon still anywhere in the Earth's shadow at all.
So outside of that 31 to 37 days, it's completely above or completely below Earth's shadow.
And that's what happens most of the time.
And our shadow is always there. And it's about the size of, what did you say, your fist? You'd say about 4 fingers probably worth.
Yeah.
And that shadow's always there. And on most months, the moon, like Ron said, goes above it or below it.
But you see here, it has to be within that little distance, as you see on the slide here. As a matter of fact, it takes the Earth's shadow about 31 to 37 days to go across that distance right there, which means that if the moon only takes 29 days to go around, it's going to get in that shadow at least twice during that period. But you may not see it because it will almost certainly be a penumbral shadow, and we don't see those very well. Hard to see. It's only the total eclipse part that we see. So to be even a partial lunar eclipse, you have to be closer to the node. So here's how close you have to be. Within that range, you have to be closer to that node to see, and that's only 24 days worth of the Earth's shadow. And that's the place where you see a partial or total lunar eclipse. And you have to be even closer to see a total lunar eclipse.
Which we have tonight.
Which is what we're
doing
tonight.
If you have clear skies.
So you have to be like this close. You see, if you're any farther away from that crossing point, the moon cannot get totally into that umbral part of the shadow. So we had a question, I think, from the internets, from someone about...
I'm going to remind everyone, too, please send us your questions, your comments, your observations. We're clouded out here in San Francisco. It's touch and go, but if you have a clear sky, please send us what you see and ask your questions. Which...
There you just saw the eclipse from the Griffith Observatory in Los Angeles.
Yes, so our live view right now is from Los Angeles. Luckily, they have clear skies down there. Slightly hazy, but...
we should start to see that umbral eclipse pretty soon. So I think that we have...
here we go. Stephanie Langdon writes on Facebook, what are all the different types of eclipses? Now, because we're covering a lunar eclipse tonight, we're going to take Stephanie's question and refer to those three types that Ron talked about, those three types of lunar eclipses, the penumbral, the partial, and the total.
Right.
And there's a lot of curiosity about how frequent they happen and which one's more rare. People like to guess why this is rare and why this is special. But you have a great breakdown. I believe you have a slide that sort of breaks down the frequency of each of those types of lunar eclipses.
Why don't you take it?
Well, all eclipses, as Ron, this is for 5,000 years worth. Now, I don't know, Ron, do you have a 5,000 year lunar eclipse manual?
If you
Can we get a shot of Ron's?
Yeah, check out this book. This is NASA's big book of lunar eclipses. This has every lunar eclipse in it from 2000 BC to 3000 AD. So 5,000 years of eclipses. It takes a book that thick to even show them in little tiny pictures.
And tonight's eclipse is in there, I assure you, and the next couple of years are. But roughly it's about a third of the eclipses that of lunar eclipses are penumbral, about a third are partial.
Let's show the slide.
And slightly less are actually total. So they are slightly more rare, but yeah, we have a great slide that.
So there you can see for all the eclipses in 5,000 years, there's 12,064 eclipses.
And
yeah, go ahead.
And some of you have written in saying, how rare is this? Is this something that's super rare? We'll get into the super blood wolf moon eclipse, what makes that rare. But to tell you the truth, there's going to be another total lunar eclipse visible from San Francisco in 2 more years. But that doesn't mean that they don't happen pretty frequently here on Earth.
Right. I don't see much umbral eclipse happening from Griffith yet. Hopefully that'll happen soon. Hopefully they're not showing us a still slide.
It is Hollywood. You know, you never know. You might be.
I'm going to trust Griffith. Those are good people down there.
They are great.
So if we go back to our slides again, here's just the situation that you see most of the time. This is from March of this year, upcoming. And here you can see the little tiny moon passes way above the shadow of the Earth. It doesn't actually, most of the time, this is the situation. It's either above or below the shadow, and so it never goes into eclipse. If you look at kind of an outside view, here you can see kind of the orbit of the Earth around the sun and the orbit of the moon around the Earth, and you can see it's tilted 5 degrees. And so there's two times of the year.
That large blue square, that's the ecliptic you mentioned earlier. The ecliptic is that plane that the Earth goes around the sun.
Right.
And for this alignment, to make eclipses possible, the plane of the moon needs to intersect at those nodes that you had mentioned before. And this does a great job of
Right, so you can see here that the only time you can have eclipses is at the near and far position of the orbit of the moon, where the tilt is such that the moon is near one of those nodes. And that's true for solar and lunar eclipses. So if we move and look at this as seen from the surface of the moon.
Oh, from the surface of the moon, like if you're a Buzz Aldrin. Happy birthday, Buzz.
Happy birthday, Buzz.
89 today.
Here's what it would look like if you're on the surface of the moon. You see the Earth kind of rolling by there. The Earth is rotating.
This is what Buzz would see on the
look
near
at the
side
rim.
of the moon.
Look at the rim of the Earth. It's kind of red. We'll talk about that a little bit later. So that's the view from the moon. And let's quickly check out the view from the Earth. Here's the view from here's the view from the sun. So here you can see the moon moving into the Earth's shadow as seen from the sun. If you're going to land on the sun, do it at night.
There you go.
Sorry, old planetarium joke.
All right.
So let's take a look at what Griffith is seeing.
So this is a live view from, there we go. This is a live view from Los Angeles. You can see the umbral phase of the eclipse starting. That rim you see, that curved line of that shadow, that is the shadow of the edge of the Earth. That's the world's largest shadow puppet, Ron. You couldn't make a shadow puppet larger than that. So yeah, we're a couple minutes into this. We're about 12, 15 minutes into that phase. And over the next, 45 minutes, that'll slowly sweep across the face of the moon. So
we'll keep our eye on it.
We'll keep our eye on it. All right, so we're going to switch over to a live feed of the Griffith. And we have some music accompaniment too as well.
Excuse me. There's going to be, we're going to have a sonifiication, which is one of our staff members here. Wayne Grimm has done a sonifiication. He's taken the image of the moon and manipulated it in the computer. So what you're about to hear is music that's generated by the moon itself.
And of actual topography, like the surface features 3D topography of the moon Wayne uses to create this audio piece. So we'll
see you again in 15 minutes.
Yeah, send us your questions and comments. Thank you.
And we're back here at the Exploratorium. Before we go any further, we should let's go back to that live view from Griffith Observatory in Los Angeles.
Wow, what a difference from 20 minutes ago.
Yeah, you can really see that the shadow of the Earth is curved. You can see it's taken a nice bite out of the moon. You'll never see this kind of phase, and I'm using that advisedly with air quotes, though you can't see me air quoting. You'll never see this without an eclipse. This kind of phase just doesn't exist unless you're having an eclipse of the moon. So you have another question, don't you?
Yes, Jacob Pounds from Memphis writes, there's a glowing ring around the moon. Is that the beginning of an eclipse? Now, Jacob, there's two possibilities here. You may have seen some haziness from our shot at the Griffith Observatory in Los Angeles. But there's also a likely chance that being in Memphis, with it being quite cold, middle of winter, you might have seen some ice crystals, a glow around the moon. You can see this on basically any time the moon's out. You can sometimes see this glow around the moon. That's caused by ice crystals in the upper atmosphere.
Could be haze in your atmosphere, too.
Could be haze in the atmosphere. It could be your TV screen.
Ice crystals usually make a big kind of rainbow-like ring around the moon, not close in, though. So if it was close in, probably haze. Or if you were looking at the Griffith Observatory view, high clouds, cirrus clouds, most likely the answer.
And Ron, so what we're hearing a lot about people is this is the super blood wolf moon eclipse. I know that's a bit of a mouthful. I think we're going to take some time here to sort of parse out what makes it super, what makes it bloody, what makes it wolfy. Wolfy?
Wolfy.
Wolf-like?
Wolfy's good. Wolfy's good.
So take
Let's
it away.
go to our slides then. So we go to our slides, and we're going to now talk about this super blood wolf moon. So the question here is, we're going to take that apart. We have to parse that out. So let's just start with super. So what makes a moon super? Well, first let's look at the orbit of the moon. Now this kind of magenta circle is not the shape of the moon's orbit.
Looks like a circle.
That is a circle.
That's a circle.
Just as tall as it is wide. The moon's orbit is actually a little bit squished. It might look like this blue circle. So it's a little bit wider here than it is tall. Now, if we put the Earth and the moon into this picture, you'll see that the Earth is kind of off to the side a little bit. It's at something called a focus of that ellipse. You can go and Google that. And if the moon moves along that blue line, and as it moves along the blue line, sometimes it's farther away, right there. We call that the apogee. And sometimes it's closer in, and we call that the perigee. G for geo, by the way, close and far away from the Earth. And you can see there that the far distance, the farther away distance is 251,000 miles, and the close distance is 224,000 miles. So there's a difference. It's a difference of 27,655 miles. So at the close approach, perigee, the moon is 27,000 miles closer. Now go ahead.
So what is that, being closer, is there an appreciable distance?
Well, if I get closer to you, for
size.
instance, you get bigger to me. And the same thing is true of the moon. So here are some pictures of the moon at perigee and at apogee. And you can see there is a difference, that at its near point, the moon is substantially larger. And if we, let me just slice them in half and push them together so you can compare them there. There you can see that it's quite a bit bigger. As a matter of fact, it's about 14% bigger when it's at perigee, and that is tonight. The moon is at perigee, very close to tonight. And so that's a supermoon. When it's far, it's at apogee, and it's also about 30% dimmer, although we have a hard time seeing that. Even though it's 30% dimmer at apogee than it is at perigee, if they're both full moons. It's really hard to see that.
And Ron, supermoon is a relatively new term, and it's not actually a scientifically recognized term.
No.
When I first heard it, it referred to it was the full moon, of which there's 12 or 13 a year. The supermoon was the full moon that was closest to perigee.
Yes.
Now it's kind of taken on this meaning where anytime there's a full moon close to perigee, we call it the supermoon. A supermoon. In fact, this year we have 3 supermoons in a row: January, February, and March.
The supermoon is as if the moon had a marketing agency working for it.
That's true.
So yeah, so we are having a supermoon tonight, and it happens to be a full moon at the same time, and it happens to be an eclipse. So that's kind of a coincidence of three things happening at once. Now, because the moon is moving in an elliptical orbit, it actually sometimes moves faster. It moves faster at perigee and slower at apogee. So we actually can peek around both sides of the moon. And because it moves 5 degrees north and south, we can peek above and below the moon's north and south poles as well. So if you look at the actual motion, if the moon could be full all the time, it would make this kind of motion. Now, each time it gets big and small, that's 1 month. And so you're seeing it here over a period of a whole year, and that allows us to see about 60% of the moon's surface, not just the half that's facing us, but a full 60%. And that's called libration or nutation of the moon. So let's move on here. We need to look at now what the... let's take a look at the moon first.
Let's take a look at a view from Los Angeles. Yeah. It's more than halfway across the face. Again, Ron, why don't you explain real quick, how come that shadow line isn't sharp, like a sharp, crisp line like you would with a lamp? It's kind of got that fuzzy edge.
It has a fuzzy edge because the sun, the thing that's casting the shadow, is big. And big things cast fuzzy shadows. If the sun were a point of light, like a star, it would cast an absolutely sharp shadow, but it's not. You can try this at home. Take a light bulb, screw in a light bulb in a dark room, and you'll notice that your shadows are fuzzy because the light bulb is big. And so some of the light goes around the top of your finger and the bottom of your finger and makes a fuzzy shadow.
And this happens on the sidewalk too, even in full sunlight, right? If you look at your sidewalk shadow, it's kind of got that fuzzy edge, and that's just because sunlight's making its way around you.
Yep. So let's go back to the slides here, and we'll talk about now what the blood moon is. Now, if we go outside at a sunset, during a sunset, here's a picture of sunset.
A blood sun.
This is a blood sun.
But people don't seem to call it that.
This was actually taken from Lick Observatory down in San Jose. And you can see there that if the sun has to go through a lot of our atmosphere, the blue light scatters out first, leaving us with the red light. Mm-hmm. So if it has to go through a lot of atmosphere, you kind of get red sunsets.
And so that phenomenon, Rayleigh scattering, that's essentially what makes the blue sky blue.
That's what makes the blue sky blue.
Makes the blue sky blue, and it makes sunsets and sunrise red.
Right, because the sunset you're looking at through more of the atmosphere, and so more of the blue light is gone by the time it gets to you because it's already gone through a huge amount of atmosphere on the horizon. So if you went to the moon and looked back at the Earth again as the Earth progresses through the shadow, through in front of the sun, what you're going to see is sunset all the way around the Earth. Again, this is Buzz's view.
This is Buzz's view. And that our atmosphere, from this distance from the moon, our atmosphere is very, very thin, like paper thin.
Yeah.
And so those are half sunrises and half sunsets. That's a combination of 25,000 miles of Earth's sunrises and sunsets being cast down on the moon.
So the sun's coming out there, so you can see the moon light up there again. And we're still in the penumbra, and we're about to exit the penumbra right there. So that's the end of the eclipse as seen from the moon. But if we go look at the Earth from above, you would see that the Earth's shadow gets cast out into space. It's a huge, long cone, as you were mentioning. How long was it?
I believe 870,000 miles, so more than 3 times the distance to the moon. Our shadow goes out into space, and normally we don't see it because it's not being cast on anything.
So if the Earth did not have an atmosphere, that would be a sharp shadow.
That would be a sharp shadow.
But the Earth has an atmosphere, and so red light kind of gets scattered into that shadow, and as the moon moves through that shadow, in total eclipse, it'll turn kind of a blood red color. So, hence the blood moon. We don't see it brightly lit. When it's fully in eclipse, we see kind of a blood red colored moon.
But this is interesting. So a lot of people ask, what color is the moon going to look tonight? And we don't know fully, right, during an eclipse, because I believe it was in the 1920s, French astronomer André Danjon said he wanted to quantify how dark an eclipse was. Was it red? Was it dark gray? Did it have like a turquoise hue to it, which is actually possible too? So that how red it's going to turn, we don't know what it's going to be like in the next hour. So you have a great slide here. This is the Danjon scale. It's a 5-point scale. It goes from 0, which is essentially a completely dark moon, no red, And that's actually possible. That happened, I believe, 30 years ago. There was a volcanic eruption in the early 90s, Mount Pinatubo, and it cast so many particulates in the atmosphere that not even the red wavelengths of light could get through the atmosphere. And that completely robbed the moon of any light, sunlight, and it disappeared.
So you can see here, it varies in brightness from, again, very, very dark, which is a 0, to 4, which is a copper orange color. And that all depends on the weather and how many particulates are around the edge of the Earth.
And this is a great reminder for you watching on Facebook Live. Send us your observations. Tell us what color, with that scale, that Danjon scale, that 0 to 5 scale, if you think it's more towards the red end or the copper, sort of salmon-colored, russet color, let us know. Tell us what you think. Maybe it's going to look different to different people. It's not science. It's just observation. So.
We have no way of knowing.
Yeah.
So let's take a look at that moon again from Griffith Observatory. See how well it's progressing. Very nice.
Oh, here we go.
It's quite nice. I could look at this all night. Well, I guess I will.
Now, a lot of people will ask that dark shadow, is there red light in that dark shadow right now? And there is, but cameras need to expose, not for the darkest things, otherwise we wouldn't be able to see any of the surface features on the moon. But right now it's sort of exposed for the mare of the visible face of the moon. So not until totality will people be able to adjust their cameras to the sensitivity needed to get all that red light.
The white part of the moon there is hundreds of times brighter than the dark part. So you can't, the eye might be able to, but the cameras cannot do that.
And we're about a half an hour out, actually 30 minutes exactly, 30 minutes from now, that shadow, that edge, the limb of the Earth's shadow is going to completely pass over the face of the moon. So that's going to be exciting, and that's when we can start seeing some of the colors.
Okay, so we have one more word left in our super blood wolf moon, and that's wolf. So let's take a look at why it's called a wolf moon. Every month has a different moon in it, and
no blood moon though.
No blood moon.
So there's no chance that we're ever going to have a blood moon.
A blood squared moon?
A blood squared moon.
No.
We have a cold blood moon if it was in December. That would be.
We could have a cold blood moon. That would actually be really cool. In January, it's called a wolf moon, and that's mainly because people have thought that wolves will howl at the moon most in January. It's around beginning to form wolf families at that point, so wolves are howling to mark their territories out and warn other wolves away. And so that's it. January is the wolf moon.
We have a super blood wolf. It's not a super wolf
moon. But you notice, by the way, September and October also can be called the harvest moon because that's when the harvest occurs as well. So
that's great. So the next total lunar eclipse that's coming up is actually in May. So when that happens, it will be a blood flower moon.
A blood flower moon.
A blood flower moon.
Yep.
That's in 2 more years.
So we're going to go back now to the eclipse from Griffith Observatory and with Wayne Grimm's sonifiication.
Send us your questions
and
comments.
See you in the next half hour.
Thanks.
And we're back here at the Exploratorium for our coverage of the total lunar eclipse. Let's go back to that eclipse and just check it out real quick now. There we go.
We're about 11 minutes away.
Yeah, from totality.
From totality. So that tiny little sliver of sunlight that's still hitting the edge of the moon over the next 11 minutes is going to absolutely disappear. And you can already start to see hints of that reddish russet color that's coming up in the shadows there. Our friends at the Griffith Observatory, I just want to say again, thank you. We had not anticipated clouds and rain here in San Francisco, but luckily Los Angeles has clear skies. So this is just a great view here in California.
If you're ever down in LA, go to the Griffith Observatory. Really great museum, fantastic planetarium. Check them out. So you can see they've actually changed the exposure on their camera here because the white part of the moon is all washed out now, and we're beginning to see some of the dark side of the moon, the eclipsed part, the part that's in the umbra right now.
And so once that phase starts in 11 minutes, it's going to continue for over an hour.
A little over an hour.
So that's not to say it's going to be the same color for that entire hour. It may change depending on the color of red and where the shadows enter and exit the face of the moon. So we'll find out. And if you have a clear sky, the view right now of the moon, please send us your comments. Tell us what colors you're seeing. We had some people writing in on Facebook telling us that they're starting to see a reddish tinge to that shadow. So keep those comments coming.
Just want to also thank Wayne Grimm. He was providing that sonifiication that you were listening to. That was taken from actual lunar data being processed live while you were listening to it. So let's talk a little bit about the phases of the moon. This is something that confuses a lot of people. So if we talk about the phases, this is kind of what you would normally consider phases of the moon. These are pictures taken almost every day of the phases of the moon. It goes from these little fingernail kind of slices to a full moon and back to the fingernail slice again. But let's take a look at the actual geometry that goes on there. If we look at the moon and the Earth, and the sunlight's coming from one direction, in this case it's coming from the left-hand side of your screen, you can see that the left-hand side of the moon, the left-hand side of the Earth are both lit up, and it has an unlit side as well. And that we get different views of the moon from the Earth. So here we see the moon moving around the Earth, and you'll notice that the lit sides always point towards the sun. But what do we see if we look at the moon from the Earth? So here, if we look at the moon from the Earth, all we're seeing here, we don't really see it. All we would see is the dark side of the moon. And I'm not referring to the Pink Floyd album. There's always half the moon that's dark. Here, we just happen to be seeing the side that is dark. The lit side is on the other side. As a matter of fact, if you're looking at it from the Earth here, you're looking straight into the sun as well. So the side of the moon on the other side is lit, and we see nothing. And we call that the new moon. Now, if we let the Earth rotate a few times, a few days, and the moon will move and orbit a little bit, and now we're about a few days later, and if we look from the Earth, you can see a tiny slice. See that tiny slice on the top there? We can see that from the Earth. Only a tiny sliver, but the rest of the moon we see is still in darkness. And that's a little tiny slice is getting bigger and bigger, so we call that waxing. And we see a sliver, and we call that sliver the crescent. So the crescent moon, a waxing crescent moon, we see after the new moon. This is 3 or so days after the new moon.
And you'll see this in the western sky right after sunset.
You always see this in the western sky after sunset. If you see, often in fictional places, you'll see the crescent moon at midnight. Never. That's wrong. The crescent moon is only seen right after sunset or right before sunrise. We'll get to that. So 3.5 days later, we rotate around a little bit, and now, viewing from the Earth, you can see half of the moon lit from our point of view, and the other half is in darkness. We call that one the first quarter moon. A couple of reasons. One, what you're seeing lit, you're only seeing 1/4 of the entire surface of the moon lit, and the moon has also gone around 1/4 of its way around the Earth here. So,
Ron, this is also a great time if you have a new telescope or even binoculars. This is a great phase of the moon to look at the moon.
Absolutely.
Because the sun is coming perpendicular to the angle that you're looking at the moon, the shadows of the craters and the features on the moon will be elongated.
Especially along that light dark line, that terminator.
The terminator line, that's right.
That's a great time to look at the moon. By the way, since we're a quarter of the way around, this moon rises a quarter of a day after the sun sets. So 6 hours. The first quarter, sets 6 hours after the sun. So the Earth has to turn another 6 hours for this moon to set. So the sun sets, 6 hours later, the first quarter moon sets. So moving right along, in another few days, the moon moves another few way around. And now, if you look at the moon, it's mostly lit. There's a little sliver that's not lit. Actually, it's a dark crescent. You might even think of it that way. But here, we're seeing most of the moon lit. It's still getting bigger. It's still waxing. And this is a phase that's called the gibbous phase. It comes from a Latin word gibbous, which means hump, because the side of the moon that's partially lit there has a hump on it. Moving along, another few days. And now, right there, looking at it from the Earth, you can see the entire surface of the moon lit, like we do tonight, except for the fact that we have an eclipse. And that is the full moon.
And speaking of an eclipse, I think maybe now we should cut over to the Griffith Observatory feed. We're almost, look at that tiny little sliver. The phase of the moon tonight, it's still full. The phase is full all night long. This is just the very last bit of the penumbral portion of the Earth's shadow. Umbral, sorry. But the last portion of the penumbral part is like fading out. We're starting to see some of those deeper, rich red colors, and it's still a full moon.
Still a full moon.
It's still a full moon.
It's a fully eclipsed moon.
It's a fully eclipsed moon. So
almost. So we're at, about 5 minutes away from the fully eclipsed moon now. 4 minutes away.
And we'll cut back to that feed in about 5 minutes.
Yeah, so let's complete our orbit around the Earth here. As the Earth rotates 3 or so times, the moon moves into a new position, and now, again, we're seeing the moon mostly lit. A little crescent is not lit, but it's the opposite side that's not lit. And it's getting smaller now. It went from full to gibbous, and so that's called a waning gibbous moon. By the way, we forgot to mention the full moon, since it's on the opposite side of the sun from the sky from the sun. Rises as the sun sets. So the full moon always rises as the sun sets. And some of you may have observed that tonight. Moving along, another few days. And now the moon has gone 3/4 the way around its orbit. We can see half of it lit, but notice it's the other half that we're seeing lit now. This is the third quarter moon. And it rises at midnight, and it sets at noon.
And that's less than ideal for sky watching. Unlike the first quarter where it's right there, way high up in the sky. The third quarter you have to wait up past midnight.
We're going to go back and take a look at the moon again. We're getting there. They've increased the exposure here, so you can begin to see some of that coppery color on the moon. That's beautiful.
Thank you again to our friends down at the Griffith Observatory for providing this live feed for us.
The moon here at the Exploratorium is teasing us. It comes out through holes in the clouds, so we have no opportunity to actually set up our telescope. So let's go back. Let's quickly finish our phases here. We now can only see a little tiny sliver of the moon. Most of it is dark, and we call that the waning crescent. And so as we continue along now, we're back to the new moon, and we go all the way around, and we can see the entire cycle of the moon's phases. Often people will put this into a calendar.
Oh, a lunar calendar. That's right. I have a little.
I think Adam has a lunar calendar here that he can show us.
Our friends at earthsky.org produced this beautiful lunar calendar. Let's see if I get the whole thing in here. So unlike typical calendars that break up by month, this shows the phase of the moon for all 365 days of the year. This is 2019's calendar. I also have 2017's here. You want to pull that one out from behind? You can see
2017.
Slightly different every year, but you can kind of see that procession, those cycles and patterns of full moons and new moons. And what I like about this calendar is there's a little key that indicates when apogee and perigee, which we talked about before, when eclipses occur. And so you can get this at earthsky.org. Support them. They're great friends of ours.
It looks here. Okay, so the months here are columns. They're not rows. So this one over here is January, so we are right here.
We are right here, and in fact, right here in Los Angeles, we're going to go to a live feed right now. That view, look at that. The last sunlight has about
a minute away from totality. And you'll notice that the edge near the lit is still kind of grayish because, again, these shadows are fuzzy. They're not sharp-edged. So in about a half hour, we'll be at maximum eclipse, and it'll be probably much deeper in shadow at that point. So we'll get a better view. Oh, it looks like they increased the exposure there a little bit again. So now we can begin to see some of that red color. And
it actually kind of looks like even a brown copper. That Danjon scale that we pointed out before, it's basically up to the eye of the observer what colors you see. If it looks more red, copper, let us know in the comment section what it looks like to you and what sort of colors you see.
But let us know what it looks like to you with your eyes, not looking at our screen, because we want to know what your observations are.
And despite this still being a supermoon, oh look, they're lightening it even more. Despite this being a supermoon, if you go outside unaided and you put your thumb up in the sky, stick out your arm like you're hitchhiking up to the sky, you could still cover the moon with your thumb, quite easily in fact.
Maybe almost like with your little finger, actually.
With your little finger, even I've heard an eraser of a pencil.
The moon is actually only a half a degree across in the sky. It's actually pretty small. It happens to be exactly the same size as the sun, but we'll get there too.
We'll get there, yeah. It's 400 times smaller than the sun, but 400 times closer. So
yep.
That's a nice coincidence.
That's really going nice. I have a slide here of a student project that did phases of the moon, but they did it with Oreos. I always just love that slide.
But no red Oreos.
No red Oreos. This wasn't an eclipse. The full Oreo there is not in eclipse. So, just one more thing I wanted to talk about here before we let you go, and there's two different kinds of months. There's something called a synodic month and something called a sidereal month, and they're just a little bit different. Our months are based on the lunar cycle. Here,
our moons.
Our moons, yes. We misspelled it. Here you can see the Earth and the Moon and the Sun, and they're all lined up in a straight line. That has a word for it, doesn't it?
Syzygy.
Syzygy, yeah.
Syzygy, it's a great Scrabble word. It's like a...
Score a lot with that, a lot of Z's in there.
ZY.
But here, you can see they're all in line. So this would actually be a new moon. This would be actually a case of solar eclipse, not lunar eclipse. Now, a sidereal month, the moon goes around the Earth one complete time. Now, by the way, look at the arrangement here. If you're standing on the Earth, looking past the moon, you see the sun, and you see a star in the distance, off in the great distance. Let's let the moon go around the Earth once. So here we go. The moon moves, the Earth moves too. So there, the moon has moved around the Earth one complete revolution, 360 degrees. And if you look out in the same direction, you'll see that star, but you won't see the sun. Why? Because the Earth has moved in its orbit and the sun is no longer in that direction. This 360 degrees around the Earth, this one orbit, it takes 27 1/3 days, and it's called the sidereal month because it's lining up to a star. To the next time you line up with a star, sidereal means star. However, if you look at this, the moon is not lined up with the sun. If you want to go from new moon to the next new moon, we have to let the Earth go a little bit further in its orbit, let the moon orbit the Earth a little bit as well.
2 more days.
Now, the moon and the sun are both lined up in the sky, and that is from full moon to full moon. It takes 29.5 days, and that's kind of what our months are based on, 29.5 days. And that is called the synodic month. So let's go back to the Griffith view of the moon. It's beautiful there. You can see there that it looks in their view kind of a coppery red color. To me, it looks kind of coppery. If we had our moon up in the sky here, which we do not, we could compare it in the real sky. Please give us your observations.
And while we're looking at this view, Ron, let's talk about some of the features that we see. The rabbit in the moon, the man in the moon, those dark spots, the mare, that's actually younger material. Those are extinct lava flows.
Giant lava flows.
Giant lava flows, and those were actually the preferred areas for some of the lunar lander missions.
The first ones.
The first ones, they preferred to land on this nice flat mare, and whether or not you see a rabbit or a man in the moon or whatnot, that's it's gonna get slowly a little darker red over the course of the next half hour to 45 minutes.
There are no mare on the other side of the moon, only on our side of the moon. There is one basin that has something that looks a little bit like a sea, but not completely. Now, by the way, since you mentioned the landing of the moon, that was 50 years ago. July 20th, 1969 marked the landing on the moon, and we will be celebrating that here at the Exploratorium. So keep on your browsers and find out what we're going to be doing in July. We'll have some really fun exhibits, as we mentioned earlier.
It's a moon month.
It's a moon month.
It's
yes.
a moon. It's a moon month.
And
it's also 50 years of the Exploratorium, too. I mean, the Exploratorium opened in, was it August of 1969? That's shortly after the lunar.
It's open to debate.
It's open to debate when the actual first day was.
We did open in 1969. We're going to have a giant moon hanging here. I forget how big it is. Maybe Nicole can yell to me how big that moon is going to be.
5 meters.
5 meter balloon we're going to have here.
Balloon
giant
diameter.
Moon. So it's and I'm also building a Lego Saturn V. We'll have that here too.
Awesome. And we'll have telescopes and hopefully clear weather then, and we'll have the telescopes out, and we hopefully then can provide live images of the moon. So yeah. All right. Thanks again for tuning in to Griffith Observatory's live feed of the lunar eclipse. We're going to switch over.
We'll be back at 9 o'clock.
All right. Take it away. Thank you. All right, welcome back. Ron, this has been a great view. We're 20 minutes into totality. We have about another 40 minutes of totality to go. Sometime in the next 10, 15 minutes, we're going to hit peak totality. And I don't know about you, but I've been noticing that white, bright cap sort of rotating over from the right-hand side of the moon over to the left. So you can tell the moon, despite it being that red, russet, copper color, it is moving through the shadow a little bit. Once again, thank you to our folks down at the Griffith Observatory for providing this wonderful feed.
Beautiful feed. And that white part, that lighter part, will probably never go away because we're not going through the central part of the shadow. We're kind of skimming along the northern part of the umbra. And so you'll see that, again, as Adam says, move around as we proceed through the umbra. As the moon moves, you don't normally see the moon moving in the sky, but it actually does move in the sky. It moves its diameter about every hour.
About every hour.
Amazing.
And from one day to the next, the moon will actually rise about 50, 52 minutes later every day. And you know, this brings up a good question when people say it's the full moon tonight, and someone will say, no, it's tomorrow's the full moon. But really, the full moon happens at one instant. It's that period when it goes from getting larger or getting more lit to less lit. It happens at an instant. So sometimes that instant actually is tomorrow in Europe, or it's on the other side of the globe. But basically any day, plus or minus from the full moon like it is, it essentially is as bright and as full as the moon will get.
We have a question from the internet that I think we can answer right now because we don't want to go away from the moon right now. Emily Kim said, "What makes the light and dark patches on the moon?" And I think we just barely touched on that a little bit earlier. The dark patches on the moon are called mare, which means seas. And they used to think those were kind of oceans, but they're not. They were in a sense oceans of lava at one point, and those are much younger and they're darker than the mountainous part of the moon, which is much brighter. The brighter part is usually called highlands because there's so many mountains in there and lots of craters. But that part that with all the craters actually reflects more light from the sun, and so it looks brighter to us here on the Earth, whereas the lava is kind of new lava and it's just darker rock, so it looks dark to us. And you can see that kind of looks like circular basins. It looks like lava, something came in and hit the moon, and then the lava came up and filled these circular impact regions.
And when people talk about the color of the moon, if you look at a full moon on a dark, clear night, it looks white. It looks bright white. And really, that's just a testament to how bright the sun is. Because actually, for people who are on the surface of the moon, the surface of the moon is this dark gray. I've heard it described as worn asphalt. Or
like a briquette.
Like a briquette. But we have a great exploratorium exhibit here called Bright Black. It's one of my favorites. If you ever want to sort of dissect what makes that moon illusion, why is that dark gray object appear so white in the dark sky, you can check it out in our central gallery.
Speaking of moon illusions, often people will say that the moon is much bigger when it's on the horizon, like you see in this photograph right here. If we bring up the slide there, and it looks huge on the horizon, or I have another slide here that was taken by a friend of mine. He had to really calculate how to get the moon right next to the Stanford radio telescope, but he caught that, and look how giant that moon looks. Well, actually the moon on the horizon is the same size as it is in the sky, 1/2 degree across, and the way you can actually determine that is to just take a series of pictures. I found this series of pictures right here, and you'll notice that as the moon rises against the buildings there, it stays the same size the whole way up, about 1/2 degree across.
And that's actually from an eclipse. You can see the...
That may have been an eclipse in, well, maybe not. It may have been just smog low on the horizon too.
That's true, similar effect.
I don't see any shadow on the moon there really.
That's true, that is just
so the moon illusion is something that's actually, people talk about a lot. And another thing that people, kind of a myth about that I want to kind of dispel is when you've seen the shadow move across the moon tonight, and it's always been round. And that's actually an early proof that the Earth was a sphere, because the only way that you could get a circular shadow moving across the Earth, no matter what time it occurred, would be if the Earth had a circular cross-section, no matter what direction you looked at it from. And the only shape that has a circular cross-section is a sphere. So if you believe in the flat Earth, then you would believe that, watch your screens now, that this should be what an eclipse would look like. as the flat Earth passes over, casts a shadow on the moon. But that is not what we see. So let's go back to the Griffith view of the moon. And so unfortunately, I don't think that the Earth is flat, just because the lunar eclipses actually do provide us with that evidence that we can use to prove that the Earth is round.
So right now, if you were on the face of the moon, and any of these points on the moon, if you were standing on any of these points on the moon, looking back at the Earth, you could not see any sight of the sun, right? All this light is being refracted through Rayleigh scattering. The long wavelengths of red light are being bent around that thin onion skin of atmosphere of the Earth and making its way to the moon. Now we see it as red because that little bit of red light that makes it to the surface of the moon reflects off that sort of dark gray and still makes it back to your eyes and this camera down in Los Angeles.
What you'd see from the moon is is a dark Earth with a bright red rim around it. And in this case, maybe a kind of a coppery rim around it. I've seen this before. I've also seen the moon much darker red, and I did see the total lunar eclipse when Mount Pinatubo in the Philippines erupted, and that was a very dark eclipse. It hardly had any light coming back from it at all.
And that Danjon scale that we alluded to earlier from the French astronomer André Danjon, one of the reasons he wanted to know why some eclipses were dark red and some were dark gray was, I believe he thought that he could ascertain something about what the sun's activity was doing at that time. And now it turns out that we know more about what the atmosphere is like, what sort of particulates and the height of those particulates. It's really fascinating. So there was no way to predict this exact color. We had a lot of information about when it was going to start and when it was going to end, when the mid-eclipse was going to happen, which we're going to come up on soon, I believe in the next
5 minutes.
About 5 minutes will be the peak of totality. So that little light cap on the top, it's going to be at its absolute smallest in about five minutes. So for all you out there in Facebook, send us your questions, comments, observations, wherever you are. You don't need to be in Los Angeles or the Bay Area. If you're in the Bay Area, you're probably seeing what we see, which is the marine layer. But anywhere else, send us what you see. We'd love to hear.
One thing we really don't have time really to talk about tonight is tides. The moon is really responsible for tides on the Earth, as is the sun, but the moon even more than the sun. And with the moon as close to the Earth as it is at perigee, and right now we're actually fairly close to the Earth's, it's called the perihelion. We're close to the sun. So the sun has more effect on our tides. The moon has more effect on our tides. So tomorrow, and also at full and new moon, that's also when you have more high tides and low tides. And all three of those things come together tomorrow and around tomorrow, and we're going to have king tides. And if you're interested in king tides and you're in San Francisco, come on out to the Exploratorium in the morning. We have a king tide walk. So you can come out and we will go on a walk. We'll head down the Embarcadero here and take a look at the king tides, and hopefully we'll see them washing, well, maybe not hopefully, but we'll probably see them washing over the Embarcadero. This is something that's a kind of a concern for us. We're here on the Embarcadero ourselves, and actually we're now in the middle of a project to rebuild the seawall, which helps keep the tides and the king tides from coming over onto the land portion of the city.
And what I've heard is the king tides of today are the high tides of tomorrow. So it's a good 20, 30 years from now to see what sort of those high tides are going to be like. We can experience those now as king tides.
Right. So we're going to return you back to the view from Griffith Observatory, and in about 3 or 4 minutes we'll be at maximum eclipse. Now, as I mentioned before, the shadows are not sharply defined because the sun is a large source of light. They're fuzzy edges, so here you can see in the current view that the top edge of the moon is closer to the edge of the umbral shadow than the bottom of the moon. The bottom of the moon is closer to the middle of the shadow. And so you see a gradation there of brightness. And you see that during most eclipses, except for that one coming up have the figures here. In 2029 is going to be kind of like a super central eclipse. We'll all have to wait for that a little bit. 2029 is a few years away yet. Actually 10 years away. So in 10 years, we'll have a super central eclipse. So maybe we have another question here we can answer.
Yeah, Howard Scully says, how often do total lunar eclipses occur as opposed to partial or penumbral eclipses. So we had maybe alluded to this earlier. How many eclipses can you have, lunar eclipses can you have in a year?
I believe every time the moon is near the node, you can have 2. They don't have to be umbral eclipses, partial or total, but they can be penumbral. So that would be twice a year, which would be 4 lunar eclipses during the year. And it's a little bit, since the shadow of the Earth, shadow of the moon, rather, on the Earth is much smaller, you can have less of the solar eclipses, about, I think, a maximum of like 3 solar eclipses per year.
And we have 2 more lunar eclipses coming up later this year, but they won't be total like tonight's is.
Yeah.
They'll be penumbral. The next total lunar eclipse visible from here is going to be May, you mentioned earlier, May 26th.
Let's see, I think I have it here.
Of 2021?
May 26th of 2021 is the next total lunar eclipse for us. And we'll get to a slide on that a little bit later on.
Let's take another question from Facebook Live. Nicole from Putney, Vermont says, does the color of the moon get affected by air quality?
That's a great question.
That is a great question. As you mentioned earlier, Mount Pinatubo in the 1990s, that sent up a lot of particulates into the sky, and that actually prevented those long wavelengths from getting. So the color, this color that we see during the eclipse, that red, the quality of air as far as particulates go will actually affect how much light gets through, just as sunsets and sunrises can vary in colors. For those of you in California, of course, the devastating wildfires we had last year, noticed some pretty dark red colors you would not normally expect to see because of the amount of particulates and the amount of light that was being scattered by those particulates.
Yeah, larger particles scatter the redder light for us. So air quality does matter, especially where particulates are concerned, aerosols. Particulates can be many different things. They can be smoke particles, they can be sand and dirt in the air, they can be salt kicked up. If you're near the shoreline, it can be salt kicked up into the atmosphere. It can be carbon from burning, like in the Amazon and the Congo and in Central Africa. You can also sulfates. Which volcanoes do a lot of sulfates, and also coal burning can affect air quality. So all those things can put particulates or aerosols into the atmosphere and change the quality of the eclipse that you'll see.
Great question. Thank you, Nicole. So we're still here. We're getting really close. I think we've actually reached, it's now 12 after 9 here in the Pacific. This is peak eclipse. This is now, the moon is passing through the umbral portion of the Earth's shadow. And this is basically as dim as it's going to get. From here on out, what we're going to start noticing is that bright cap start rolling over to the other side, and slowly the sort of peach, what would you call that? It's almost like a sand color, will start to get brighter and brighter. And the moon's basically it's on its way to leaving now, the umbral shadow.
We've completed half of the eclipse. So we're halfway there. Again, this is from this footage is from Griffith Observatory in Los Angeles. If you're ever down there, go up into Griffith Park. Take your car or take the bus up to Griffith Park and check them out. They've just remodeled. Well, it's not just remodeled. They remodeled about 10 years ago, and they have a brand new, some really wonderful exhibits up there, and a great planetarium. Do some great stuff up there. So be sure to visit Griffith Observatory. So I guess we will leave you now until 9:30. We'll just put up our pictures of the moon from Griffith, and you will be listening to the sonification of actual lunar data by Wayne Grimm, one of our artists in residence. See you at 9:30. And we're back here at the Exploratorium for our 9:30 version of the lunar eclipse, the total lunar eclipse. Take a look at that moon again. Let's just go right to it, and you'll notice now that that bright portion of the moon, which used to be up on the upper right portion, is now on the upper left part of the moon as the moon moves closer towards the edge of the shadow. And that should happen when?
In about 15 minutes. So we're about 15 more minutes of 13 more minutes of totality here. Starting in about 13, 14 minutes, you're going to start seeing that bright white cap grow larger and start sweeping across the face of the moon again. And we'll sort of basically run the whole process that we've been doing for the last 2 hours in reverse.
Right. So we'll be exiting the eclipse at that point. We were talking about supermoons and the moon being closer and the moon being farther away. Well, how do you measure the distance to the moon? You can't just take out a tape measure. And so let's take a look at that, about the distance to the moon. If we look at that, the moon, here's actually a good scale model of the moon. Here the Earth is about the right size at 8,000 miles across, and the moon is about a quarter of that at 2,000 miles across. And that distance that you see between them is correct. Rarely do you actually ever see this in a book done this way, because there's just too much space between the Earth and the moon. The average distance to the moon, because remember it gets closer and farther away by a little bit, the average distance is about 239,000 miles. And that's actually, here's an easy way to remember that. The moon is about 30 Earth diameters away from the moon is about 30 Earth diameters away from the Earth.
Another fun way to do this is if you take a nickel, just a US nickel, and tape it to the wall, if you stood about 7.5 feet away, that's about the size to scale that the moon would appear. And you can do that little trick we talked about earlier with holding up your thumb.
Right.
And you should be about 8.5 feet away, 8 feet away, and you'd be able to block 2 of those nickels on the wall.
So how do we measure that distance? Well, on Earth, if you want to measure the distance of something, you could use a tape measure, but you can just go out to like Home Depot or something like that and get one of these really cool laser tape measure devices. And what these do, it's actually pretty cool. It has a laser right in the front there, and it has another lens with a photocell behind it in the front as well. And it sends out a little pulse of laser light, and it measures how long that pulse takes to get back. So here it is kind of broken down. The bottom thing is a little laser, and the top thing is the photocell. The laser sends out a beam, it bounces off something like the moon or a wall in this case, with the thing you can buy at Home Depot. And you measure the time it takes to go out and the time it takes to bounce back. Now, if we know that time, the time it takes to go out and back, and we know what? The speed of light, which we do know, it's 186,000 miles per second. If we know those two things, we can easily determine the distance to the wall or to the moon, and that you just take the speed of light and you multiply that times the time. Now, in the case of measuring the distance to the wall or measuring the distance to the moon, you'll notice that our laser pulse went to the moon or to the wall and back again, so it went twice the distance. So the distance is actually half of that factor that you multiply speed times time, because you can see there's a to and from. Now, on the moon, the Apollo astronauts left some very special reflectors. Here you can see on the left-hand side the whole reflector, and a little close-up on the right-hand side.
It's not large either. You can see the footprints.
No.
The footprints that are actually still there.
It's actually 2 different sizes of them up there. The Apollo 15 left a much larger one up there.
Oh, okay.
But
well, the photoreflective cells here, so this is essentially a wall section that will always return the laser back in the direction it came.
Yeah, this thing is called the Lunar Ranging Retro Reflector, and 3 of them are on the moon. One was left by Apollo 11, one was left by Apollo 14, one was left by Apollo 15. Now, each one of those little circles you see there has a prism in it. It's called a corner cube prism, a retro-reflecting prism. And when light comes into that prism, it reflects inside such that it reflects back exactly in the same angle, so it reflects back to the source of light. So it reflects, it's kind of like your bicycle reflectors. Your bicycle reflectors, those plastic things, those round plastic things, have a bunch of these corner cubes in them as well. And they're designed, excuse me, to reflect the light directly back to the source. And when you do that, you just have to send some laser pulses to the moon. Now, this is a lot harder than you might think. The first people to do that were our buddies down at Lick Observatory above San Jose. And here, here you're looking at the original Lick Observatory building. The big dome there is the 36-inch refractor, the Great Refractor Dome. That's not what the instrument they use. They use the 3-meter refractor in the dome you see here, and they sent out pulses of argon laser light from a very large telescope inside there, a 3.1 meter reflector. It's called the Shane reflector at Lick Observatory. And they did this first in 1969, right after they left that reflector on the moon. What's interesting here is that beam, when it gets to the moon, is about 4 miles wide. And they're trying to hit a little tiny thing, which means it's actually pretty hard to find the reflector. It took them a while to find the the prisms. It's kind of like aiming a beam. It's like trying to use a rifle to hit a moving dime at 2 miles away. So it's actually pretty hard because the moon's moving, remember. The reflected light is way too weak to see with your human eye. So when they send like 1,000 photons at the reflector, actually they send millions of photons at the reflector, only about 1 photon comes back. So they have to send a lot of pulses. They have to send, they only see like 1 photon every few seconds. That's really hard to do.
And this was not a AA battery either.
These were super powerful lasers.
Super powerful lasers in that they traveled 500,000 miles.
They would blind you on their way out, but you couldn't see them on the way back.
In about 4 seconds, right?
So yeah, about 2.5 seconds.
2.5
seconds.
It takes
2.5 seconds to go out and back.
And back.
And this has given us some of the most precise measurements to the distance of the moon that we have yet. They have been able to measure the distance to the moon to within about 1 millimeter. A millimeter. That's like very, very, very small. 1 millimeter. It's like just put your fingers almost together and that's a millimeter. That'd be like measuring the distance between Los Angeles and New York to 1/100th of an inch. It's pretty accurate. And that data is actually really important. Knowing the distance to the moon, you can learn a lot about the orbital dynamics of the moon, and you learn a lot about the Earth that way as well.
And that it's changing too.
Yeah.
We know because of this sort of data that the moon is actually moving further away. So in the distant future, solar eclipses won't really be a possibility.
Let's go back to looking at our picture of the moon. There we go. You can see it's getting a little brighter there on the edge. As it approaches the edge of the shadow. Again, these shadows are very fuzzy shadows, so you're not going to see any defined edges here. And yes.
You can actually make out some of the craters too, in the lower portion, in sort of the dark umber area of the lower part in your image. That's actually a pretty famous crater, the Tycho crater, named after Danish astronomer Tycho Brahe.
Yeah.
But yeah, the way the mare are starting to change colors on the upper left-hand portion it's really a sign that we're leaving that totality section of the umbral eclipse.
You were mentioning that the moon, actually because of the tides, because of the pull of the tidal bulges of the Earth, is actually being accelerated. It's moving further and further away. The moon's moving faster and faster, therefore it has to move further and further out. And it does that by a few centimeters a year. So the moon now is smaller than it was last year, but not by much. But in millions of years, the moon's going to be far enough away that it won't be big enough to ever cover the sun. You will never see a total solar eclipse. We live in a really nice time right now. We get to see total solar eclipses, but only barely. So
that's why they only published this book you have. It's only published through the year 3000.
3000. The 5 millennium canon of lunar eclipses. Well, these are lunar eclipses. So lunar eclipses are going to be for a long time. That book's going to be valuable for quite a while. But NASA hasn't published it for millions of years yet, only for out 3,000 years. Good book. Bestseller. I don't think you can get it anymore in paper form. I think that they don't print it anymore. You can get it online at the NASA's Eclipse website, which, by the way, is a great resource for information about eclipses. Just look up NASA Eclipse, and I'm sure that you'll be able to find it quite easily.
Also want to recommend MrEclipse.com.
Oh yeah, that's
Fred Espenak is sort of the unofficial eclipse person.
That's right. Well, Fred actually is responsible for all the diagrams that you see on NASA's website as well. So he's still calculating stuff for NASA, but I believe he retired from NASA, and he's sort of independent now. And Mr. Eclipse, yeah, it's really great sites.
MrEclipse.com. So this live image from Los Angeles right here, it's sometimes hard with eclipses where there's nothing moving. There's nothing to really tell that this is happening right now. I think someone mentioned earlier they'd seen a plane go across. Was that true? I think it's kind of fun when these little observational hiccups happen. It sort of keeps you grounded. That's for.
Every once in a while you can see it move when they're adjusting the exposure on the camera or they're repointing it or something. I don't know what telescope they're using for this. They're probably not using the big refractor in the dome down there at Griffith Observatory. They just changed the exposure a little bit. And as the moon comes out of eclipse, they want to keep the white part properly exposed as well. So what you're seeing now, the moon get darker, is not actually happening in the sky. That's happening in the camera. So don't worry, the world is not about to come to an end.
Should we take another question from Facebook?
Sure.
Amorous writes, when is the next total lunar eclipse happening? We mentioned this earlier, but I think because a lot of people are concerned that this is rare and that they might have missed their chance to see if they were clouded out, for instance. When is their next total lunar eclipse visible here from the United States, from the Western Hemisphere?
Well, we have a series of slides about a few of the next upcoming eclipses. We can do those now, I guess, if we want.
Yeah, but if you want to put in your calendar right now, I'll tell you right now, it's May 26th, 2021, and I think we said that's a flower moon.
The flower moon.
That's a blood flower moon of 2021. Not sure if that's going to be a super moon, but as we've seen tonight, it doesn't require a super moon to have an eclipse.
It's almost certainly not going to be a super moon because the perigee won't be anywhere near May by that time.
And actually being a super moon kind of shortens the amount of time. Because it's larger, it shortens the amount of time that it could be in that umbral shadow.
It's bigger compared to the shadow itself.
And likewise, too, if you have a super new moon or a super moon during the new phase, that actually can lead to really long solar eclipses.
Yep.
Some of you might remember the solar eclipse from 2017. That would lasted about 2 minutes.
Yeah, it was pretty short.
It was pretty short. Had the moon been larger, the solar eclipse would have lasted even longer. And I think the longest a solar eclipse could be is about 7 minutes.
7 minutes.
7 minutes. So, and I believe the solar eclipse in the United States in 2024, I believe that's April in 2024, that's going to be about a 4-minute totality. So for anybody who missed the solar eclipse in 2017 in August, fear not, you'll have another chance in 2024 and it'll be twice as long. So it'll be worth the wait for sure.
We have some slides coming up to show that.
We have some slides coming up. But anyway, we are now at 9:43. We are officially at the end. We're at the, as Ron alluded to earlier, the U3 point. We're now leaving the third contact point, and we're leaving totality. So now the Earth is going to start, the moon is passing out of Earth's shadow and is going to be fully illuminated in that top left corner, and that bright white face is slowly going to take over. So essentially we're watching what we watched before in reverse, the mirror image of that.
Remember that the moon is doing the moving here.
The moon is doing the moving. Our shadow is
moving, but it's moving in the same direction as the moon.
That's true.
So, but the moon's moving faster, and the moon moves about its diameter every hour. It's kind of hard to see that in the real sky unless you're really observant. If you have a little, like binoculars or a telescope, and you can see the moon near a star, you can watch it move relative to the star in the sky, and that will give you a better clue as to the actual motion of the moon. But we don't normally see that. It's like watching the hour hand of a clock.
It becomes very apparent in something called occultations. An occultation is when the moon passes in front of an object, like a star, or sometimes a planet. And so sometimes if the moon passes in front of a planet like Saturn, they call that the occultation of Saturn. And it's really fascinating. You can see it through binoculars or a small telescope, but you'll actually watch what appears to be Saturn or a planet disappear behind the moon, but fear not, that's the moon moving quite fast.
That happens gradually. When you do it with a planet, you can actually watch the planet or the moon disappear behind the moon. But excuse me, if it's a star, it's almost shocking. If you watch a star go behind the moon, it approaches the edge of the moon, and as it gets to the edge of the moon, it just goes blink, because stars are essentially points, and so it just goes out. And it's kind of a surprising thing when you first see a lunar occultation of a star. It's kind of a fun thing to do, and you can look up online. And those are, by the way, very location specific, because as you move around on the Earth, the perspective that you get. If you're up north, you're going to look over at the top of the moon. If you're down south, you're going to look underneath the moon. And so the moon seems to shift a little bit in the sky depending on your location. So stellar occultations do depend on where you are on the Earth. But check it out if you can. I mean, I'm sure you can find some stuff online about it.
And once again, this live view from the Griffith Observatory in Los Angeles. Looks like they're adjusting their camera right now. Send us your observations, your comments from what you see, where you are, wherever you are in the country, the Western Hemisphere, anywhere really, wherever you are. Antarctica, out at sea, who knows. Tell us what you see, what does it look like, even try to take a cell phone picture through binoculars. It doesn't take a lot of fancy equipment. One of the nice things about the moon being so large is that you don't need a lot of magnification, and you don't really need a big telescope because you don't need to gather a lot of light. So yeah. It takes a little practice, but you can experiment with a cell phone and even binoculars to get a great view of the moon. So if you have any great pictures, post them in our comment section.
And by the way, you can take your cell phone and put it right at the eyepiece of a binocular and take some really great pictures. Just put your cell phone right up against the eyepiece. It might be hard to point, but
it helps to have a friend, because once you get that perfect alignment, somebody can reach over and actually take the picture for you. It always seems like when you go to reach and take the picture,
do some experimentation. Helps to mount your binoculars on a tripod if you can get that. Look online, find a tripod mount for your binoculars. So I think that we're about done until 10 p.m. So we'll come back in about 14 minutes now, and we'll sign off here and see you in about 14 minutes.
And don't forget to send us your questions, comments, observations on Facebook in the comments section, and we'll do our best to get to them with our last segment coming up, I believe, in 20 minutes.
So enjoy the sonification by Wayne Grimm of the moon's surface.
All right, welcome back. As you've probably noticed, our totality portion of the show is starting to end. Let's go to that live view in the Griffith Observatory in Los Angeles, which is actually not that different from our view here in San Francisco after 3 sort of clouded hours. We have pretty much the same view here. So what you're seeing now here is that bright dome that was on the upper right-hand portion is sort of now on the upper left-hand portion. This is the moon. This is the full moon now coming back into full sunlight. Those red colors that you saw before, they're still there, but the way this camera is exposing it, it's sort of darkening all of those colors.
It also kind of sharpens up the edge of the shadow too.
That's true, yeah. So that curved shadow, as we mentioned before, that is the curved edge of the Earth's shadow. That's that bullseye we talked about. It's a cone shadow that extends almost 900,000 miles out into space, and about 240,000 miles away, it's this large, dark shadow disk. So the moon is on its way, well on its way to passing out of that shadow, and we're on our way to getting a full moon again by the end of the night.
Yep. So I wanted to talk a little bit about the orbit of the moon. Some of this might be a little of a refresher from some stuff earlier. So here you can see a slide, and we wanted to first get some terminology correct here. Notice that the moon revolves around the Earth, and it rotates on its axis. So if it rotates and the axis of rotation is within the body itself, that's called a rotation. And moving around another body, that's called a revolution. As a matter of fact, Copernicus, when he first observed that concluded that the planets move around the sun, that was created a what? A revolution. It's kind of where we get that term in that usage. So if we look at the moon moving around the Earth, again, sizes and distances are not to scale here. And let's start the motion up. You'll notice that the moon keeps one face towards the Earth all the time. Now, many people think that because there's only one face towards the Earth at a time that the moon doesn't rotate. But if you look here, you can see clearly that the moon is rotating. And if I put an arrow there on the moon facing the Earth, that arrow is rotating around as the moon revolves around the Earth. So rotation and revolution, but this also shows that the moon is rotating. It just rotates once every time it revolves once around the Earth. So if we look at that orbit, the orbit is not a circle like this magenta circle. The moon's orbit is kind of slightly squashed. It's an ellipse. And if we throw the Earth and the moon into there, the moon can be farther away or closer, as you can see here. When it's farther away, we call that the apogee. And when it's closer in, we call it the perigee. And it varies by about 27,000 miles, close to far away. You can actually see that, and that's what gave us the supermoon tonight. We're at perigee tonight. So here you see the moon at perigee, the large one on your left, and the moon at apogee, where it's farther away, is on your right. Kind of split them and shove them together there. You can see that the difference is actually pretty marked. As a matter of fact, at perigee, it's about 14% bigger than it is at apogee, and up to about 30% brighter. But that's actually really hard to observe with the naked eye. So if you look at the distance and the change of the distance from the Earth, here's kind of a graph that might be kind of hard for you guys to see out there. But this up and down blue line with the dots on it, that's the distance, and it changes. It gets closer and farther and closer and farther, and you can see there that the full moons are the solid dots, and the new moons are the little X's. And when you have a full moon and it's close to the Earth, when it's near the bottom, that is a supermoon. And when it's near the top, that's, I guess it will be an anti-supermoon.
A mini-moon.
A mini-moon, a micro-moon. Again, because the moon moves in an ellipse around the Earth, we get actually a peak around the sides of the moon and around the top and the bottom. And so if you look at the actual motion of the moon, it kind of does this. But this would have to be assuming a full moon all the time. But it's actually going through phases. Every time it gets big and small, that's 1 month. The sun, by the way, we get closer and farther away from the sun as well. When we're close to the sun, that's called perihelion. And when we're far from the sun, it's called aphelion. or aphelion. I guess I put the P and the H together and call it aphelion. And here you don't see that much because the difference of the distances is not that much. So let's just cut them in half and squeeze them together, and you can see there we go, that the sun gets bigger and smaller, but only just slightly because the distance only changes by about 3 million miles or so.
And that happens, so the sun at perihelion, that happens in early January.
Right,
and
about now.
About now, we just passed it actually, January 3rd. Unrelated to the solstice actually, which is kind of a misnomer. Then that actually changes, it precesses over time, and that the perihelion won't be January 3rd.
Right, it doesn't get hot in the summer because we're closer to the sun, because it actually happens in the middle of winter.
And the sun at aphelion, that actually happens beginning of July, around July 3rd or 4th. So if you're a frequent solar observer, you may be able to measure and notice the difference, but for most of us, it won't make much of a difference.
Right. So if we look at kind of the outside view again, you can see here that the moon's orbit, those tilted squares, they're actually tilted about 5 degrees to the Earth's orbit around the sun, which is that large blue plane. And on the left and the right, the new moon and the full moon, actually the new moon's shadow passes over the Earth, so we don't get total solar eclipses, and the Earth's shadow passes over or under the moon. And those are not good seasons for eclipses. The only good seasons are every 6 months when the plane of the moon's orbit is tilted such that the new moon or the full moon can either cast a shadow on the Earth or have the Earth's shadow cast on the moon. And so you can see that we have eclipse seasons separated by 6 months here.
And that changes over time too. Something we won't get into tonight, but if you want a little further reading, sort of astronomical rabbit hole would be to read about Saros cycles, a 18-year, just a hair over 18-year process where that plane itself is actually rotating and changing and pitching.
That tilt of the moon's orbit actually rotates around in an 18-year cycle. So most of the time, here you see the moon moves above the shadow of the Earth. This is actually from this coming March, where there will be no lunar eclipse. Let's go back now to the moon, check it out, from the Griffith Observatory in Los Angeles. And they're supplying our view tonight. There we go. And now we see we've progressed quite a bit more out of the umbra of the Earth, of the Earth's shadow. And we only have, let's see, the fourth contact happens at
about 45 minutes, at
45 minutes.
10:50. And thank you again to all you people on the East Coast sticking with us. We know it's after midnight. It's now officially Monday. But those of you in LA, you got clear skies. We haven't seen a cloud, I think, in the last 2 hours, so we've been pretty lucky with this feed. So at that point, 10:50, so in about 45 minutes, that dark line, that edge of the Earth will be completely off the surface of the moon. The moon is actually moving to the left in this image, and it's moving away from that shadow. So we're going to be able to watch that over the next 20 minutes or so.
And excuse me, if you're in San Francisco, go outside. It was clearing up here.
It is perfectly clear right now. I can see it with my own eyes.
See it with your naked eye. It's nice to watch it on the monitor. It's actually warmer to watch it on the monitor, but go outside, get a little chilled, and see the total lunar eclipse as it emerges from the shadow of the Earth.
And I think one of the things, what I like about lunar eclipse is it gives this depth and dimension that you never really see in full moons, because in full moons, usually that light is hitting you square on. It's hitting the face of the moon. You can't really see craters and shadows, and it kind of looks kind of featureless. It's not actually a great phase of the moon to look at through binoculars or a small telescope. But tonight, with the sort of the dimming around the edges, it really adds a neat depth, and it feels more like a sphere. It looks more like a sphere, which is something that sometimes looking at stuff in the sky,
you mean the moon's not flat too?
I mean, it's not flat. It's not it adds that nice depth to the whole thing.
It's very cool. It's so much fun to watch these things. I've been watching them for decades and decades now.
And we've gotten a lot of Facebook comments on the sonifiication by Wayne Grimm, a sound artist here at the Exploratoriums, who's taking some of this 3D data about the surface of the moon and turning it into this musical art piece that you've been hearing during our inner sessions. And maybe we'll ask Wayne after this next break to tell us a little more about that.
One commenter said that it was zombie ambient.
Zombie ambient. It's a whole new genre. Look for zombie ambient Spotify list coming to you in 2019 by Wayne Grimm. But yeah, keep the questions coming, comments, observations, wherever you are. Tell us what you see, and if there's any other questions, we've covered a lot, and we're happy to go over things.
We could do some. How about some superstitions? Someone was asking about superstitions. Who was that?
Let me pull up that question right here. Lisa Hicks Damansk writes, "What superstitions about the eclipse are still recognized today?"
Yeah. This is nice stuff that we can do with the moon on the screen, so you don't miss any of the eclipse. Oops. Well, maybe not. We'll get that moon back in a moment.
That's right. So we're talking about eclipse superstitions. Obviously, it's 21st century. We have a lot of data about why this happened. We could predict down to the second when certain things are happening. But that always wasn't the case. For something as unpredictable as an eclipse, for shadows moving across and colors, sometimes red, sometimes brown, it's understandable that people developed superstitions. And I can't say that I practice any of them, but luckily we have the internet, and Ron was able to pull up some of the best superstitions that we could find.
So I'm going to apologize because I'm going to have to read from a piece of paper here because I don't remember a lot of them. But I'm just going to take my piece of paper here. We'll share this.
Sure. And if you have superstitions yourselves, like it'd be great for you to submit your superstitions. We're going back to the Griffith Observatory.
Okay, great. So
here.
we can talk about the superstitions with the moon on the screen. That's even better.
And actually, I like this because this little sort of crescent shaped here. You mentioned earlier the crescent phase and how that varies from this. This isn't a crescent phase, although it looks like a crescent. That radius of curvature on the right is from the Earth, and the one on the left is from the moon.
Right.
That is not a terminator line. That's the line between a total solar eclipse and a partial solar eclipse if you were standing on the face of the moon.
Right.
So let's launch into some of these superstitions.
So, Tibetan Buddhists, they believe that the good and bad deeds that you do during a lunar eclipse are multiplied tenfold. So I hope everybody out there is doing some good deeds.
According to South African myth, the sun and moon fight during an eclipse, understandably. It's up to the people to come together and encourage the celestial bodies to resolve their feud, ideally in an hour
I think
or
that's
less.
actually a pretty common belief. Many Native American tribes say that lunar eclipses are a sign of transformation to come here on Earth, based on their belief that the moon controls and regulates our planet.
And the next one's pretty popular. With the total lunar eclipse we had back in 2015, 2.5 years ago, that's when I first heard about blood moons and various apocalyptic warning signs. Anyway, a common belief is this widely shared saying here in the United States about total lunar eclipses comes from the Bible, according to Joel Book 2, verse 31. The sun will turn to darkness and the moon to blood before the great and dreadful day of the Lord comes. Or Rayleigh scattering allows long wavelengths of red light to make it to the moon.
That's in the Bible?
Wow. No, I added that. That was the Book of Adam.
Oh, okay. You know, the Bible says that pi is equal to 3. Just 3.
Just 3, okay.
Just 3, yeah.
Make for interesting wheels.
So, yes, impossible wheels. In India, people avoid cooking, eating, or drinking during lunar and solar eclipses. They believe that food spoils faster in the absence of the sun's light and could bring on indigestion. I hope not, because we just had some wonderful pineapple upside down cake here baked by my friend Benjamin over there. It's also believed that if you cut yourself during an eclipse, you bleed for longer and it can leave a scar for a lifetime.
I'm not going to try to
We
find
stayed
out.
away from knives.
We stayed away from knives, yeah. We cut the bundt cake with a plastic knife. This is another popular one. I like this. The Incan civilizations believe that blood moons occurred when a mythological jaguar attacked and ate the moon. To drive it away and stop its slaughter, the people would shake spears at it and make their dogs bark at the night sky, which, quite like a wolf moon. Today, sky watchers still give a nod to this ritual by watching lunar eclipses with noisemakers in hand to, quote, scare off whatever is swallowing the moon.
So go outside right now, make noise, and you might be successful in returning the moon to full phase by the end of the night.
It's definitely because you screamed at a shadow.
Everybody go outside right now. Just the neighbors won't mind, I promise you. Oh, in several cultures, expectant mothers are advised to stay indoors when the moon turns dark red for fear that it may curse their unborn child. They should also rest from housework, since using a knife or other sharp object is believed to cause birthmarks. I like that one.
I like that. Many people believe that the full moon affects human behavior and psychology. The Latin name for the moon, luna, is the root of modern words like lunacy, lunatic, and even loon, as in crazy as a loon.
I'm not sure about that last one.
We think that's a bird.
I think the loon is a bird, like a loony bird.
Ron and I have been
although maybe the bird was named after the moon.
That's true, and someone spelled it wrong. We're fact-checking the internet here. Anyway, all right, so it's now 15 minutes after 10. This live feed from the Griffith Observatory never fails to impress. They've been very lucky down there. No cloud cover. I haven't seen a plane go by. Looks like they're adjusting their image right now.
Or it's windy.
And yeah, we're going to have Wayne Grimm sonification sound piece take it away and enjoy the last little bit of totality here.
And thank our friends down at Griffith Observatory. We'll see you again at 10:30.
All right, we're back. It's now 10:30 here on the West Coast. Only about 20 more minutes left of totality.
Yep.
Thanks again to our friends at the Griffith Observatory for that amazing view. You can now see that most of the umbral shadow of the Earth is now way to the right side of the image. So now the moon is on its way to totally leaving that umbral shadow to the left. And we also got some great questions here. Davis from Birmingham, Alabama says, when is the next eclipse? Ron, you have the perfect amount of slides to address this.
Davis, you are lucky because I just happen to have slides on future eclipses. So let's check those out. The next lunar eclipse that's going to happen is on May 26th, 2021. So get this into your calendar. And this is just an eclipse visibility map. We haven't actually shown a visibility map yet. Here you see the United States up there in the, excuse me, I have to cough for a moment. There we go, I got it muted this time. You see the United States is kind of up there in that gray area, and that means that we're not going to see the entire eclipse. We're sort of, California at least, we're in that little P4 area, which means we're going to miss the penumbral part of the eclipse. We'll see most of the eclipse, but it will be a very late evening. The moon will set before it's completely out of eclipse, at least for the United States. If we go to the next lunar eclipse, which will occur on May 16th, 2022, there the situation is a little bit different. There you can see the U.S. is now on the other side of that white area. We're still kind of in the gray, and that means that the moon will be rising already in eclipse. In California, you can see that we're in that U1 area, which means that we already would have passed the first part of the partial eclipse as the moon is rising. So that's May 16th, 2022. Moving along, the next total solar eclipse that we'll see all of.
Total lunar
eclipse. Did I say solar? I'm sorry. The next total lunar eclipse we'll see is on November 8th, 2022. But you can see that we're kind of on the right-hand side of that white area there, so it's going to be late. Totality starts at 2:16 a.m. for this eclipse, so it's going to be a much later one for us here in California, and even on the East Coast, the moon will have will be set for part of that. Now, just moving quite far into the future, I wanted to talk about this one. This is the most central eclipse, and that's coming up in 10 years from now, June 26th, 2029. And this is one where the moon almost goes perfectly through the center of the shadow. Now, our totality tonight lasted for an hour, but it can last as long as an hour and 47 minutes if it's perfect. This eclipse will have totality lasting about an hour and 41 minutes, so actually an hour 42 minutes, so only 5 minutes short of the absolute maximum it can. Let's take a look at that situation on the eclipse diagram. So here we see tonight's eclipse, and you can see where the moon is kind of scooting through the northern part of the shadow there. It's not centrally located at all.
And it's ascending. You mentioned before the ascending nodes and descending nodes. This would be in tonight's eclipse an ascending node eclipse.
So it's already above the ecliptic by the time it gets to the shadow here. But in 2029, here's the situation. Here, the middle of the eclipse happens almost right on the node. So you can see the moon progresses right through the center part of that eclipse. And so that's going to be, it's almost perfectly central eclipse. An hour and 42 minutes, where the maximum is an hour and 47 minutes. So let's move from lunar eclipses to solar eclipses, because this is kind of important for us. Here's a map of the path of totality for the next total solar eclipse on July 2nd, 2019. You can see all those blue circles, those are the shadow of the sun as it passes over the Earth. Now you can see here that mostly it's in the southern Pacific Ocean, but the very tip of it there is crossing over South America. And just coincidentally, there's a very famous observatory in Chile called the Cerro Tololo Observatory, and we will be observing that eclipse from the Cerro Tololo Observatory this coming July 2nd, so you'll be able to tune in. We are just sending some telescope folks there. We're not going to do a big production from the site. We're just sending some telescope folks, and we will be just webcasting that eclipse coming up July 2nd, 2019. So put that one on your calendar. The next big one for the U.S., however, for you to go outside and see, well, you'll have to travel a little bit, is on April 8th, 2024. And here we're going to look at it as if we were on the sun. And here what you're going to see is the moon move across the surface of the Earth, and you'll see there's a target, a little red circle with a little teeny red circle in the middle. You have to be in that little tiny circle in the middle there. You see it's dark, and that's going to come in through Mexico, go up through Texas, and pass through Oklahoma, Arkansas, Missouri, Illinois, Indiana, Ohio, New York, Vermont, and Maine before heading into Canada and Newfoundland. And by the way, this one does come in from Mexico. We're welcoming it from Mexico. And here's the path of that eclipse. So that's going to be a nice big one coming up April 8th, 2024. And if you've never seen a total solar eclipse, it's worth traveling to go and see. Trust me.
And this will be almost about 4 minutes long, too. So for people who saw the total solar eclipse in 2017 that came across the United States, that was about 2 minutes. This one, April 8th, 2024, will, at peak totality, if you're in the center line of that path of totality, you'd see a solar eclipse that lasts roughly over 4 minutes. Right. And I don't know if you have a place picked out, but I have my sights set on West Texas. Fredericksburg.
I'm going to go wherever the Exploratorium goes.
There you go. All right, that sounds great. Anyway, let's kind of talk about some of the as we're switching back here to this live image from the Griffith Observatory. Only about now 15 minutes away from the end of the totality. But although what we don't really see in this image, although it looks like a full moon on the left portion of this image of the moon, that's still in the penumbral phase. Yes. It is still greatly dimmed over a total, what would be a uneclipsed full moon. So it's still dim. It's just the comparison to that dark area that makes it seem so bright.
It doesn't leave the penumbra until 11:48. That's the real end of the eclipse. So that doesn't happen for quite a while. But we're going to watch it here up until the end of the umbral portion of the eclipse. Looks like they're adjusting the exposure there a little bit. That is not actually happening in the sky. Do not panic.
And so as the night kind of comes to a wrap, we're going to go switching back to Wayne Grimm's sonifiication data and his sound piece that goes with this. And the Griffith is probably going to keep broadcasting this through the hour, right through the penumbral. So we're going to, it looks like they're finally getting clouds there in LA. Oh, yeah,
I see some clouds passing over the moon there. We have our crew to thank here as well. Wayne, our sonification and sound guy. Phoebe, Rick, Nicole, Amaris, Liz, Wayne, and Benjamin. We actually have quite a large crew up here producing this thing here for you. And without all of them, it wouldn't have happened. So we hope that you'll...
and Cale Hazard.
Oh, and Cale. Where's Cale? I don't see Cale.
We have these bright lights on us. We can't actually see who these faces are. But yeah, the whole Moving Images team at the Exploratorium makes this possible. And they make a lot of our webcasts possible, which is really one of the best parts, I think, of the Exploratorium's
We should be turning the camera around at this point, but they won't do that because they don't like being on camera.
We shouldn't touch that camera.
No, I'm not going to touch that camera. So we're going to send you back now to Griffith, and we're going to play you out with Wayne Grimm's sonification. And we hope you enjoyed this eclipse, and hope you'll get your calendars ready to watch the total solar eclipse on July 2nd of this year. And that's it. We'll say goodbye from the Exploratorium.
Thank you.